I'm very glad to be here. It's a nice experience to meet people from different, let's say, communities, mathematical communities, which in subjects which are of common interest, and it's also very interesting for me as well. So as you can see, can you see the? Okay, that's not very. Colors are not very distinguishable. Okay, so as you can see, the topic of my course is very close. I think it was not by chance to the course of to Laurent's course. So so the motivations are similar, and of course the difference will be that we adopt different points of view. I will show. Maybe different types of results, and part of the interest of giving this course is also to bring closer to the other point of view, the PD point of view, this type of models, and see if it can motivate some interaction and in order to address new questions, for instance. Okay, so I turn it off. Okay, so this is an outline of my course. So I will be first giving a motivation. So as I mentioned, the idea will also be studying models for dispersive animal populations with different types of interactions, which could be at the ecological level, demographic level, and also at the space level, okay? In particular, in the way the interaction between these populations influences their displacement, okay? Spatial displacement. So I will then be interested in formulating and proposing some probabilistic description of the populations I'm interested in by looking at the individual level. Okay, so this really means that trying to represent the microscopic interactions, which we expect to see at some moment at some microscopic level, and the idea will be then to define a family of models, of microscopic models, using probabilistic tools, and then study what happens when we consider a large population, okay, large population number, which is quite a standard approach in the probabilistic modeling of, say, dynamics of populations, but also in lots of other domains, like in statistical physics, for instance. Okay, so in particular, we will see that we can obtain a family of deterministic models, which will be PD models, which are close to the models that Laurent will be discussing tomorrow and discussed today. So that is the purpose of the first lecture, these two issues. Then tomorrow I will study some other properties of the object, limiting object that we obtain. Okay, and I will use some tools from stochastic analysis, and in particular I will be interested in some limits of this macroscopic model. Okay, so to recover some regimes which have a specific interest or meaning from the modeling point of view, and I will also discuss a little bit how close or far we are, and in which sense these models are different from the models, the PD models, like the one Laurent is going to discuss also tomorrow. Okay. One of the interests of this probabilistic approach and this individual-based approach is that it easily leads to simulations. Okay, so the possibility of doing simulations. So at some moment, I will also show like small simulations, like toy scale simulations, which already exhibit some of the behaviors we would like to study or find in this type of models. Okay. Okay. So let's start with the motivation. So, well, it's was a good thing that Laurent's course was before mine, because he already introduced an important part of the ideas or the motivation in this setting. So, but let's say maybe in a more light way, okay, not necessarily concerned by mathematical reasons or motivations. Just let us think in a global way. What are we interested in? So we would like to describe a population or a biological community where we have several species. We have displacement in space, so they move. So you can think of animals as several of the talks you have seen have done. We will think that there are interactions between these animals, and which induce some behavior at the level of the spatial displacement. Okay, so we could have, for instance, animals being attracted, being repulsed between them, or dispersed in the sense that they just, I mean, there is no like clear direction where they go, but the effect of the population nearby makes them to disperse somewhere, in some sense. Okay. As I mentioned, we are also interested in taking into account demographic interaction, which typically takes the forms of competition for resources, for instance, and which determines or which has an influence on the way the population growth, the total mass of population growth or decreases. Okay. And possibly heterogeneous environmental conditions. Okay, so you might think of some geographical location. You can have different resources available, and the resources will depend on the geography. Maybe, I don't know, there is a river, there is the sea. So we would like in general to be able to take into account the possibility of having an heterogeneous environment. Okay. And consider the possibility of different interaction scales. Okay? So the interaction will be among different populations or inside the population, and depending maybe on specific features of each population, the way the other population influences it will depend on, I mean, can be at local scales or global scales. Okay, so we want something which gives us some flexibility to describe the interaction. Okay, so as Laurent already mentioned, these questions have been around for several decades in the mathematical community or the mathematical biology community. So, and they have been addressed mainly from the PDE point of view. Okay, so these are like some of the classic references or works in this direction. There is the work by Shigesada, Kawasaki, and Teremoto, which Laurent already mentioned, which triggered this mathematical interest for this type of models. So as you saw in the previous course, so this is the prototypical equation, the prototypical PDE associated to these models or used to formulate these questions. So you have a competition, or well, this is the reaction part, which takes into account the mass for each population of type, let's say, 1 and 2. This takes into account this accounts for the demographic behavior. Okay, so you have a negative term which is quadratic in the population, which is this one. You have a growth term which is this one, this product, and then you have this product of the two populations, which is telling you that population 1 is being affected by population 2 by the amount of individuals. Okay, so this coefficient, you have something similar in the other for the other population. So these coefficients corresponds to what is called the interspecies competition. This is interspecies competition. And you have some spatial behavior, which is, in this case, will correspond to a diffusion. Okay? So you have here a diffusion which is, let's say, autonomous for population I1. And then you have, on the diffusion coefficient, you have some influence of the density of individuals of the other population. You could also have here, inside multiplying U1, another U1, which is called the self-diffusion coefficient, which was present in Laurent's slides. And this type of interaction is what is called cross-diffusion. Okay, so this is a model which has been studied for some years already. So there are, last decade, there are several results, and well, let me just mention that the more systematic approach to this model from the PV point of view was developed mainly by Chen and Jungel, and also by Laurent, Thomas, Moussa, and Trescas. And so it's still a domain where lots of things being done. There are several questions and in different directions. And of course, Laurent can tell you much more about the PD point of view than I can do. So let me go to my specific goals in this course. So first of all, as I said, I would like to provide an individual-based description of these populations, taking into account representing stochasticity, either in the displacements or in the demographic fluctuations. So, for instance, in the reproduction, the mortality, in a way that obeys the competition for resources. And also, I would like to represent this individual displacement, which can be influenced by the density of individuals, of all species present. So the tools we use for doing this, for constructing individual-based models, are tools taken from the theories of stochastic processes. Typically, we will deal with diffusion processes, pause and point processes. And of course, the main toolbox for working with this is Ito calculus. Okay? And we also will be dealing with other kinds of processes in more complex, which are measure valued processes. Okay? So once we have this individual or a base model, the idea will be to derive a family of macroscopic models, to derive or justify a family of macroscopic models, which in the setting I will study will turn out to be deterministic models, so PDEs, or integral partial differential equations. And the idea is, of course, to recover this type of behavior, so inter and intraspecies competitions in the way Lokta-Volterra models do, and also density-driven spatial dispersal. So behaviors in the form of cross on self-diffusion. Okay. I say behavior because from the beginning we will have these models, these PDE models in mind, but we will not get exactly that. And in some sense we will get some more general models, and in some sense more particular, because you will see the tools are different, the assumptions, the kind of results we can get are different. Okay, so in a way they are complementary, and an interesting question is how to bring these 2 points of view together. Okay, so here to get some macroscopic model, the tools which we use are tools from Convergence in distribution, and also stochastic calculus, for instance. Okay. And of course, we are also interested in studying some properties of the limiting model. And as I said, we would like to understand as much as possible the connection with the available PDE models. So the tools to do that, which I will present during the course, are also stochastic, but of course, anything is welcome, because once you're dealing with the PDE, at the PDE level, it is not clear what is the, I mean, everything is welcome in order to try to go further. Okay, so, and maybe there are not standard tools, even from the PDE point of view, okay, to deal with these objects, the objects we get. Okay, so this mini course is based on a paper with I didn't mention, with Sylvie, which appeared last year with Sylvie Mellard, which appeared last year in Journal of Mathematical Biology. And there is an expanded version which I posted a couple of days ago on the archive, which contains more details on technical details, and so you can download it if you want. So much of the things I will be discussing in these two courses are explained in much more detail there. Okay. Okay. So let's start with modeling these populations at the individual level. Okay, so we'll assume our individuals are moving, they live and move in RD, and we will need to deal with measures on RD. Why? Because the way I will be representing the population will be using, in a mathematical way, will be using measures. Okay, so you can imagine that I have several individuals in some spatial domain, and I don't really care. I will not really care about which individuals these are, but I will care about their positions. Okay, so it will be natural to represent the positions of the individuals, irrespective of which exact individual I'm talking about, using point measures. Okay, so and since we will be looking at the evolution of this population in terms of this measure, I need a good notion of continuity. Okay, I will look at how this evolves in time on one hand, and on the other hand, I would like to later to take some limit of this when the number of individuals goes to infinity. Okay, so I need a good notion of being close, of converging, and the good notion turns out to be the weak topology. Okay, so weak topology is defined as the convergence of the integrals of our measures against continuous bounded functions. Okay, so you have probably seen this in other contexts. in Bertrand's course as well. Let me just recall some ways of understanding this convergence and the associated topology. Okay, so I will write calligraphic M. Let me write it like this. So this will be the set of finite measures. So they are Borel, and I will always be assuming that they are non-negative. And let's consider, in this particular case, we're going to deal with RD, but all this theory and all this point of view can also be applied in more general settings. So this in particular can be a Polish test. Okay, so here you can think of RD, which is the case at least for this part. Okay. So there are different ways of equivalent ways of describing this notion of convergence. So let me mention two other ones. So let's say Mn is a measure, finite measure. So we say, okay, it converges to weakly to this sequence converges weakly to some measure M, as was mentioned, if when I integrate against bounded continuous functions, I get convergence. Okay, so this is for all bounded continuous function f on E. But I can equivalently replace this for by functions which are bounded continuous, which are bounded and continuous at x for, let's say, almost every point x with respect to the limiting measure. Okay? And I can even replace this, can also replace this for every f which is bounded on Lipschitz. Okay. And one very nice and useful property of this notion is that it actually induces a topology, and it is a metrizable topology. Okay, so you have several equivalent metrics which induces topology, and I will be using at some moments the following. So I have two elements. And I will use I will write like this, the norm in the space of Lipschitz bounded functions. Okay? So this is like a dual norm, like a strong dual norm, but not with respect to the original space where we had the duality, which is the continuous bounded functions, but rather with respect to the Lipschitz bounded functions, besides bounded. Okay? So here in the Lipschitz norm of f, I'm taking into account both the increments. So this norm takes into account the increments. And the supreme. Okay. So I'm controlling these two quantities. Okay. And a nice property of this metric is that as soon as the original space is Polish, this space turns to be Polish as well. Yes? Ah, sorry, thanks. Of course, yeah. Thank you. Yeah, so it's the usual dual norm in this space. Okay. Okay, so let's introduce notions relevant to the model. So we will need some parameter which is called the charge capacity, which was already mentioned several times, which tells me in some sense how big can be a population which this environmental is able to support to allow. Okay, so let's say it's of the order of the population size. And then one single individual will have a weight in the total population of the order of 1/k. Okay, so as I said, the idea is to represent the individuals as being points in my domain, and the complete population I will represent it in terms of the measure which tells me where these points are and their weight. Okay, so the weight of each individual will be 1/k, so I will just take a sum of Dirac masses in the positions of the individuals. Each one with mass 1/k. Okay? So this space will represent the configuration of one population. And since I'm interested in dealing with several species, let's say capital M, I will work in the product space of these objects, okay, to represent the different species. Okay, so let me introduce some notation for our model. And let's start by the spatial dynamics. Okay, so this means that using these objects, I would like to describe the spatial behavior displacements of the individuals of each species. So I have here, I will be dealing with a symmetric non-negative defined matrix, which I can evaluate in a point where the individual will be, and this is a vector of positive real numbers. Okay, so this vector here will be associated to the idea of the density of each of the individuals, each of the species. Okay, and I will also consider a drift coefficient. So this will describe the spatial motion of population I. And I will also need a square root of the diffusion matrix, which is typically what we need when we want to do a pathway description of this movement using diffusion processes. Okay. So this square root will be called sigma. Okay, so the interaction between species or between individuals will take place through three types of kernels. So these kernels, I will call them G, H, and C. So they describe the interaction between the species by means of their densities. And more precisely, this will be, you can think of them as convolution kernels, which I will be convoluting with my measures. And I will be able to see then how population J is affecting an individual of population I at different levels. So this could be at the level of the diffusion, at the level of the drift, and also at the demographic level, okay? So here. In principle, this dependence could be, this density dependence could take place at different scales. So you might think, for instance, that these are like kernels which decay fast, but you could also take a constant kernel, okay? So in that case, I will be considering a global dependence of the other population. And we would like also to take Dirac mass eventually, okay? So you can think that these kernels control the scales at which interaction takes place and the different at the different levels, okay, for the population. And I will call Ri, so this is a function, just depending on a position, and which will tell me the reproduction rate of an individual at a given position. So, okay, so the idea will be to look at this let's say, I don't need to separate them, so I have my domain, I have individuals of one type, and then I have individuals of the other species, okay? And I'm looking at these empirical measures describing the population of each of them. So I will call new ik each of these measures for I equal 1 to m. And the idea will be to construct a Markov process which will describe the evolution of these populations, okay, with all the interactions and which I mentioned. So we will denote by NIT the size of the population, the number of individuals of type I which are alive at time t. So if you remember that each individual has a weight 1 over k, so this is exactly k times the total mass of my measure new ik. This should be a t. Okay. Okay, so each individual of type I located at some point x at a given time t will have 2 independent clocks, let's say. So these clocks will control the demographic dynamics of this individual or of the population. And the idea is to be able to describe some Lokta-Volterra behavior in the sense that I will have a competition for resources with the same population of the same type, my individual, or with individuals from the other population. Okay, so this will be done. So here, this interaction takes place at the level of the demographic events. So first, I will have what I call a clonal reproduction clock, which means that my individuals they give birth when located at position X, they will give birth to one offspring at the same position, okay, at this rate. That's the intuitive idea. Okay, and there is a mortality clock which rings at this rate. So what is this rate telling me? It tells me that I need to look at the individuals, so this is a J, of all the populations, including the same population as I, and look at their positions and then compute this convolution. Okay. So if this Cij was a direct mass, you can think that I'm really counting the number of individuals at the same point. So if that clock rings, the individual dies, which means that it is removed from my measure, from the support of my measure. And the dynamics, the spatial dynamics, will be governed by the diffusion matrix and the drift vector which I introduced. But let us look at that. Look at it from the perspective of one individual of type 1, of type I. Okay, so this is a function. If I compute all of this, what am I doing? I'm taking the diffusion matrix. Here I can put a position, which will be the position of the individual I'm looking at. Here, these are positive numbers, which are telling me the density of each of the populations near, let's say, the neighborhood of the individual which I'm looking at, and so on, and a similar construction for the drift. Okay? So, of course, this is also depending of the states of the other populations. So this is just to give the idea of what one single individual of type I sees. Okay? But of course, he's also influencing the individuals of the other populations. So this is a dynamic construction. And in order to make things work, I will make some assumptions on my data. So I will assume that the square root of the diffusion matrix and the drift coefficient are Lipschitz functions. So this is the standard framework where you can construct diffusion processes in a pathwise way using Ito calculus. Okay? So I assume they are globally Lipschitz continuous. And moreover, I will assume that the growth of the diffusion coefficient in terms of all of the population's densities is at most linear, uniformly on the position where my individual is. Okay? So the idea is to allow for changes in the diffusion behavior affected by the density of the other populations, and even allow it to be this influence to be non-bounded. Okay, so it can grow, but not too much. Okay. And the interaction kernels will be Lipschitz unbounded continuous functions. As for the reproduction rate, I will assume it is continuous and bounded as well. So R bar denotes an upper bound for all of them, the reproduction rates. Okay. So the idea to construct this process is to define, first of all, the positions of individuals. And then, so for each population type, I will have at time t NIT individuals, and I would like to construct their positions. Okay? Then I will put the direct masses on these positions, and I get my measures. That's the idea. Okay? Divided by 1 over k. Divided by k. So for simplicity in all this SQL, I will take 2 species. Okay? So otherwise, expressions are too complicated. And actually, the treatment of 2 species or any finite number of species is the same. Okay. Are there any questions or comments for now? Okay, so don't hesitate interrupting me if you have questions or I'm saying something which is not clear. Okay. Clear enough. Okay, and what are the sources of randomness? So this is the first thing we have to decide when we want to do some stochastic model in any setting. Okay, so the idea will be that I will possibly my populations will be initialized from random points. Okay. I will consider lots of Brownian motions, but I will only be using a finite number of them. So the idea is that I have 2 species, so I have 2 families of Brownian motions, and each of these Brownian motions will be driving the, let's say, capital N individuals alive at each moment. Okay. And I will use what is called a Poisson point process or Poisson point measure, which will be governing the reproduction and death events. Okay, so this is probably a less familiar object than Brownian motions for many of you. Let me just recall that what is the idea behind this Poisson point measure. So the idea is that we have some distribution of points, in this case, which are located in a 3-dimensional space. So on one hand, I will have time. On the other hand, I will have the second argument. I will have, so these are numbers, okay? So in this coordinate, this is discrete. I'm on the positive integers. And on the other coordinate, so this is theta, so this will be like an artificial parameter, which will be used to, in order that the events happen at the rate we would like to. Okay? So we will see in a while how that works, but what is important to keep in mind is that to this, so we have points here in this 3-dimensional space, and it is enough to keep in mind the following. So if you choose any subset of this space, the number of points which you will find there is a Poisson random variable. Okay? And what is the parameter of that Poisson random variable? It is exactly the measure of the set I'm looking at for this measure. Okay? So this is what we call the intensity measure. So the intensity measure in this case is very simple. I take Lebesgue measure in both coordinates, real coordinates, and here it is just the counting measure. Okay? So the idea is that I pick some subset. I look at how I ask myself how many points I find there, and the answer is it is a Poisson random variable which has parameter the measure of this set. So imagine that we have, for instance, A, B, and here I take an M. So look at this cube. So this cube, the number of points in this cube should be a Poisson random variable of parameter A, B, M. Okay? So that's the first ingredient. And the second one is that if I look at sets which are disjoint, these Poisson random variables are independent. Okay? So the idea is to put points in the space independently for different regions. And okay, there are lots of nice properties which you can derive from this definition. And yeah? And star is that I'm is n without 0. Okay. And I'll take all of them independent. Okay. Okay, so how are we going to construct these dynamics, these populations? So just for notational reasons, we are going to fix some ordering in our D, okay, in my state space. The idea will be to construct, on one hand, the times at which some demographic event takes place, and then, in a recursive way, also construct the dynamics of the populations between these events. Okay? So what we will find is that we will see is constant size population evolving continuously in space until the moment I have some demographic event, so a reproduction or a death. And that will mean that I will remove some of the points, or I will put a second point above one of the others, which I had, and then I will run again this dynamic. Okay? So the jumps mean jumps of the measure, because I will have a jump. I will change the size. So the mass will change. Okay? So the idea is the following. So at step 0, I have I will take my population to be the elements of the support of my measure. Okay? So why do I need this ordering? It's arbitrary, but it's just because I want to assign to each of them one random motion of the sequence infinite sequence I had. Okay? So it's just to have some consistent way of defining this. So recall that this is a point measure. It's a sum of direct masses, each of them with mass 1/k, which I assume to be random. So then I look at where points are located, and I run a dynamics for this vector. So the number of individuals will be fixed at the beginning. And I do this for each population. So then what I do is put in place the stochastic description of the diffusion process which I was speaking about. Okay? So from time Tm on, I look at this stochastic differential equation. So it's a family of stochastic differential equations. I will look at them. I mean, it's a fixed finite number of equations as long as I don't have a jump event. Okay? So in principle, I could solve this equation and run it until infinity in time. Okay? And I have the good properties in order that this is well posed from the stochastic calculus point of view. In particular, the Lipschitz continuity of all the coefficients which are involved. Okay? So in principle, I can do that forever, so there's no problem, but I will stop when the following happens. So I would look at one of these measures. So this was one measure Qi. So time goes in this direction. Okay? And at some moment, I will have an atom. So an atom is a point in this three-dimensional space. So if one of the measures happens to have an atom verifying the following condition, then I will jump. Then I will do the jump. And what is the condition? So the condition is the following. So the natural coordinate in my atom, in my measure, will tell me which individual suffers from, a demographic event, or is dead, or reproduces. Okay, so at any time, I will always have a finite number of individuals, and indeed, I have this number, which is the initial population size at time Tm. Okay, so if something happens above this level, so let's say if this is NITm, I don't care, I don't see it. My population doesn't see it. Okay? So the first thing I need is to have an atom at some time. So let's say now I'm running from Tm on. So I need an atom which I can associate to one of the individuals in my population. And also, I need this parameter theta to be smaller than something. Okay? So here is the idea of adapting the rate to the dynamics of the population, okay, to what's happening at the current position, the current state of the population. So the idea will be that I take theta smaller or equal than the rate. So, okay, so I have I have two measures, and I look at, so it could be just, let's say, Q1 or Q2, okay? So that means that one of the two populations has some demographic event. Okay, so this gives me an index J. And, oops. So the measure gives me, according to what measure has the atom, that this tells me what is the population which is having this demographic event. This coordinate tells me at what moment that happens. This n tells me which individual of the population, on which individual my demographic event occurs. And this theta will be used to say what is happening. Okay? So the total amount of, the total rate at which something can occur is the rate at which an individual can die, can give birth, reproduce, and the rate at which it can die. Okay? So we put a T minus here because we look at what happened just before, where individuals were just before the atom. And when that happens, okay, I have a jump time, and I set T n plus 1 equal T. Okay, so T was the instant at which I found this atom. Okay? Is it clear, the idea? Yeah?
Consider the same interaction level for both the diffusion and the grid?
Yeah, that's a mean. It should be H. It could be different. Well, it's not, yeah, in principle it could be different. Sorry. Okay, so what do we do then when I find this atom? So first, so J is the type of population on which something happened. Okay, so if I look, if I'm looking at population I and something happened on the same population, so if J equals I, this means that either one individual gave birth, either it died. Okay, and this is what is happening is told by where theta is. Okay, so remember theta is smaller or equal than r plus something, so I can split that into two possibilities. So first, theta being smaller than r, which will happen at rate this number, and that will correspond to a birth event. So in that case, my population size increases by 1, and then I take, I add one individual at the same position. So n is the index of my individual who gave birth. So I add this mass, this point to my population, and I rearrange it just to assign the Brownian motions in a consistent way. Or otherwise, I could have theta in this interval. Okay, so in that case, that will happen with this at this rate, which is the length of this interval. Okay, so this will correspond to a death event due to competition, which happens at this this rate, which depends on the populations. Okay, so right before the jump. And in that case, we remove one individual. We remove from the vector of positions. So here I have n minus 1. So n is the individual who is affected by this event. So I remove it from my vector, and I then rearrange this again. Okay. So that's the case. That is what I do when the population which is affected by the demographic event is the same as the one I'm looking at. I, index I. And if it is the other one, so I don't do anything. Okay? I don't touch my population. I just re-index them just for notational reasons. Okay? That's here. Ah, no, sorry. I don't do anything, so I just don't touch the population. And then I increase m by 1, and I iterate. Okay? Okay, so the first remark is that this... Are there any questions for this part?
So the Brownian motions,
yes.
you only rearrange them when there is a jump.
Yes, yes. And only for the population where there was some change. Okay? But just, that's purely notational. I mean, I want to deal with n Brownian motions, and which correspond to this, I mean, which is given by this n in each of the intervals, okay? It's to make things simpler, right? Okay. I mean, if I took another rearrangement of the Brownian motions, it would be in law it would be the same. Okay, so first property is that when doing this, I am defining globally a process. So why one should be careful with that? Because even though our jumps happen, I mean, you need to wait for some positive time in order to see a new atom. Okay, why is it that like that? Because in each compact set here, I will have a finite number of atoms, because it's a Poisson random variable of finite parameter. Okay, so there are strictly positive. These times have strictly positive intervals in between. But what could happen is that I have some accumulation of the jumps. So these random times are increasing, and they will diverge to some time t infinity. Okay? My process, in the way I constructed it, is well defined up to this time. Okay, so let's say 0 t infinity. But could be that this happens, so could be that t infinity is different from infinity. Okay? So at some point you must show that it is equal to infinity. Okay? So that's the idea. So okay, you're able to do that using. I don't think I will have much time to explain to do the computations with details, but the proof is related to the following property, which will also be important, and is the fact that this dynamic preserves moments. Moments of the, so this is the total mass at each time, okay? And if I assume that this total mass has some finite moment of order p at time 0, this property will propagate, okay, for finite time intervals, okay? So maybe I can say a couple of words. This, so how do you prove this? Actually, what will happen is that you can compare the total mass with the mass of a population where you have no deaths. Okay, because this has the total mass for my population has positive or negative jumps of size 1/k, and you can neglect the negative jumps, and you will have an upper bound for the population mass. And in that case, what you're looking at, of course, the rate at which these reproduction events occur is random, but you will use the fact that this reproduction rates I are bounded. Okay? So at the end, the reproduction dynamics is controlled by a branching process. Okay? So you will have at most some exponential growth of the population. Okay? So you can use that and some Ito calculus to show that the population will be controlled, and you will also be able to show this bound. Okay.
You do this for R Lipschitz or?
Here you just use R bounded. Okay. And once you have this, it's easy to derive the first property. Okay, because the rate at which jumps occur depend on, are bounded. If the population is finite, they are bounded by R bar plus the convolution with these measures. And if these measures have total mass, what I will see is that a finite total mass. What I will see is that at each time, I will be looking at some finite set here. Okay, for theta. Okay, so. Okay. Sorry.
You need a strong assumption on C, since it's just a competition. I would expect one just given on the on R, no?
Yes.
What's happening if you have no depth, basically?
Sorry, but what? Could you be more precise with the question?
You were saying that what is important is that you are bounded by the bound on R and the bound on C.
Yeah, times the bound on C times the mass. There, the masses. Okay, and when showing this, you're showing that the masses are finite in each compact interval with probability 1. Okay. Okay, is it clear, the idea? Okay, and you can also show, but I will not be needing that explicitly, that this process turns out to be Markov as we said. Okay, so it is just related to the fact that okay, I have independence from in my driving processes, so the Brownian motions, the increments of the Brownian motions, and the increments of the counting processes associated to these measures. And the only point is that my dynamics is defined in terms of the vectors, not of the measures. But it turns out that the law of the resulting measure value process does not depend on which index you gave to the, so permuting the Brownian motions or the measures will not. The levels of these measures will not change at all. Okay, so everything depends just on the measure. Okay, so in order to go a bit further with results or trying to do computations, you need to identify the good processes associated to this measure process. Okay, so we'll define the following processes. So if you're familiar with stochastic calculus, you will see that this is just. Well, this is a sum of Brownian motions. First, of the values of some function with evaluated at the positions of my population I. So that's the idea. Okay, and this is a stochastic integral. So this is what you get when you apply Ito formula somewhere. This is the kind of expression that you get. So this one, this is a martingale. So you probably saw in Bertrand's course, or you knew from before, that when you integrate with respect to Brownian motion, you get, okay, maybe not just a martingale, which is the ideal framework, but a local martingale. And well, martingales are, in a rough way, are processes which have constant expectation, but it's a bit more than that. So it's a process which, given the past, we don't expect to have some variation in the future. The best estimate of the future, given the past, is the present value. Okay, and it has nice properties because so local martingales is nearly that. You probably will have a problem with the size of the random variables you get, but the idea is that so a local martingale is something that you can truncate in a natural way with respect to the time sense, and what you get is a true martingale. Okay, so in particular, if this was a martingale, since the expectation is preserved, this has null expectation. Okay, and the martingale will be telling you, in some sense, will be isolating the fluctuations of your dynamics. Okay, what expression tells you how the fluctuations are. So you will have this kind of object, and you, in order to control or to see how big the martingale is, you need to look at the quadratic variation, and that is an object which arises in the following way. So imagine you have a martingale, and you ask, what happens if I take the square? Okay, so it turns out that the square will be increasing. That's a simple fact from Jensen's inequality. So increasing the average. Okay, but you can subtract something which is also increasing in such a way that this will also be a martingale. Okay, so the difference is that this process is increasing. Okay, so this is increasing in average, and this is truly increasing in a pathway sense. Okay, so that's what we call the quadratic variation, and the quadratic variation is an interesting object because it allows you to control the magnitude of the martingale. We'll see in a way, in terms of its fluctuations, in a way. And that comes from the fact that this quadratic variation, so you should think of something controlling the fluctuations of the process. And you can obtain it like this. So it's a sum of increments to the power 2. Okay, so in the case of Brownian motion, this is just t. Okay, and then, so since you have two sources of randomness, you will have this kind of object associated to both of them. So this is the one associated to the Brownian part, and you will have another martingale associated to test functions, of course, and to the Poisson point process, which is driving your demographic events. Okay, so the notation here is so I'm not writing Q, but Q tilde. A tilde means what we call the compensated measure. Okay, so that means that each time I integrate something, nice processes with respect to this measure, of course I will not get a martingale because this would be increasing, for instance. Okay, imagine that I'm taking something positive. So here it's not the case, but if I put something positive here, this would be increasing. Okay, so the idea is that I will subtract something in such a way that I will get something which is constant. Is constant in average, and what I need to subtract is what is called. I mean, it is exactly the same the integral of the same function, but with respect to the intensity measure. Okay. So This is noted like this, and it gives you a martingale. Okay? And you can explicitly know what the quadratic variation of this martingale is, again, in terms of the jump measure, of the point measure. And the idea is simple. It's just you take this function, you take the square, and then you integrate it with respect to the intensity as well. Okay? So here, hidden is the intensity. Remember, the intensity was counting measure. So the counting measure is here, hidden. Okay, first was time integral, which is here. Then I have the counting measure here. And the 1/k is here. And then I integrate, I compute these lengths. Okay? Okay. Okay, and I will introduce some notation. So this is the notation this is a short notation for what I will see in the diffusion part when I take test functions of my process. So I will denote by Li nu applied on F this second order differential operator where I have. So this is really the standard parabolic differential operator. And I'm taking here nu1 and nu2 as data. Okay, they are fixed. Okay, so this is a non-homogeneous, or will be non-homogeneous operator later. But here, let us imagine that I have some fixed measures, and I just evaluate this at each point x. Okay. Okay, so with this notation, I arrive at this. So this is telling me in a summarized way what the dynamics of my measures are. So what I'm doing is taking test functions, so depending on space and time, and I look at how these quantities evolve. Okay, so what I get is an expression which comes from the diffusion part. Okay, so from the dynamics of each of the individuals. Remember that I'm averaging, okay, somewhere. And here, so I'm averaging over the population I, so this gives me this. And here I have the demographic component. Okay? So this is not hard to show with like basic tools and formula of ithocalculus. So this turns out to be, so here I'm isolating something which is a nice expression in the sense that I can understand it in terms of the measures and some kind of operators. Okay, so here I have a parabolic one. Here I have some operator of order 0 acting on F. And on the other hand, on the other side, I have my martingales. Okay. Okay, and so this is true for functions being of class C1 in time and C2 in space, and for some functions with a specific, controlled growth of the derivatives, I have some nice properties which are used later for our results, which are first of all that my left-hand side here is bounded by the third moment of the total mass. Where does this 3 come from? So here is one time the measure, and here in the diffusion coefficient, if you remember, my sigma, which was the square root of the diffusion matrix, was linear in the measures, in the densities. And when I write this operator, I take the square of this matrix. Okay, so the diffusion matrix A is quadratic in the measures. Okay, so here I have something which is cubic. And on the other hand, if I'm controlling, so this under these conditions, I'm controlling my operator L in uniform in supremum norm, and if I'm able to control the moments, at all time, which I can do if I control the moments at time 0, I will control the expectation of the objects which are here. And in particular, I will have that these objects here are true martingales. Okay? These are useful remarks for everything that you need to do later. So here's the main result, the first main result. So we will assume that we have convergence in distribution of these random initial conditions to something which is fixed. So this is deterministic. Okay? I will explain in a while what is convergence in distribution, but it's actually related to the notion of weak convergence. And I will assume that at initial time, okay, so I will be doing the charge capacity go to infinity. Okay, that's the idea. I want to take a macroscopic scaling limit. So we assume that I have convergence of the initial conditions to some deterministic limit. I have a uniform control of the third order moments. And then I can conclude that my process converges in distribution in this space, which I will say exactly what it is in a way, to some function or so indeed it is a measure, it's a flow of measures which solves this equation. Okay? So what are the spaces here? So this is a Skorohod space, which is the space of Cadillac trajectories in the space of finite measures. Okay? So remember, they were Cadillac because I have jumps of the population size at least. Okay? And the limit will be a continuous function. And this is related to the fact that I will have my jumps are of size of the order 1 over k. So I will get something which is continuous. And I will get this equation. So in this equation, I have a deterministic model which takes into account the properties or the behaviors which I wanted to represent. So I have this bilinear term here in terms of the measures. Here there is something which depends on the densities as well, on the level of the diffusion. I will just say in a while what does mean, but okay. So this model, so this PDE allows for position-dependent dynamics. As we said, the coefficients of the diffusion might depend on the position. I can have density dependence that can be local or non-local. And even unbounded, because I have up to quadratic growth of the diffusion coefficient in terms of the measures. And if you assume that you actually have a classic solution, so what we get is a measure solution of an equation, a system of integral partial differential equations. So if you assume that you have a classic solution, you can rewrite the equation in that way. And if you take in particular, for instance, AI, so let's say I take BI, all the BI's equals 0, and I take, let's say I take all the kernels equal to direct masses at 0. So this is formal because I haven't done it, but if you think that these are the kernels are like this, if I take B equals 0 and I take, let's say, AI of X V1, V2 equal to alpha V1, I don't know the coefficient, but I can recover the also this is called U. This is what I call U1. 1, 1, 1, 2. Okay, I can recover the self or cross diffusion models which I showed at the beginning. Okay, so this is formal because by the moment we're able only to make this kernel go to the direct mass. And on the other terms, we still have a local type of interaction. Non-local. It's not point-wise, but it depends on the neighborhood of the point which I'm looking for. Okay, yeah, so meaning of convergence is in distribution, it is exactly this when you're dealing with probabilities instead of finite measures. Okay? So convergence distribution, you know it from probably central limit theorem, but you can also speak about convergence in distribution in arbitrary spaces. Okay? So here we have two spaces, one which is this space of measures. So one assumption is that the initial conditions converge. And as a consequence, I get convergence of this process, so of the law of this process. So the laws of these processes are probability measures in the corresponding space. And here I get this in the Skorohod space, which is the space of Cadillac paths in this measure space. Okay? Let me so I will not be able to go into much details of how this is done, but let me just give an idea of what are the elements of the proofs. So first of all, you need some. So this is very similar. You probably have seen this if you have worked in probability on stochastic processes. But if you are rather familiar with PDE tools, so this is very similar to obtaining first like a priori bounds, then showing some type of compactness of your objects, and then see that in the limit limit of subsequences, of converging subsequences, you satisfy something. I mean, which is the equation, let's say, you're looking for which you want a solution. Okay, and then if you really want to show convergence, you need to show that all the accumulation points are the same, and that is related to the uniqueness. Okay, so. So here we have a similar procedure. So the idea is to have controls of the total mass, which we already did, and then control of tails. So what does that mean? The control of tails is something you must care about when you look at measures, because one problem that can arise is that, I mean, even if you control if you control the masses of your measures, so you can have some pathological behaviors, which could be that the mass will drift to infinity in a way. Okay, so imagine you have a Dirac mass and point n. So these all are probability measures. They have so the mass is controlled. Well, you can even put a coefficient here. So you can have a n converging to something, but if this mass is drifting to infinity, you will not have a convergence. Okay, so that's one of the things you have to obtain from the dynamics. So the relative compactness of the laws is related to the notion of tightness. Okay, so tightness is really the Wood notion, is equivalent to relative compactness in this space. And in order to do that, so in the case E is the Skorohod space, you have criteria. You have criteria which you can apply in terms of simple process. For instance, the measure process integrating some nice test functions. Okay, and then you are back into the real valued processes, which are easier to deal with. Okay, and so once you know that you have convergent subsequences, you might pass to the limit in these sequences, but in a way which is compatible with your topology. Okay, so what you're able to do at the end is to take your object, your process, apply some continuous bounded function, and then take expectation and go to the limit. Okay, so the idea is, in order to identify the limit as a solution of the equation we want, again, the idea is to start with this. So here you have something which is very close. So this really looks like our equation if this was equal to 0. Okay. So the idea is that you show that this left-hand side has good continuity properties as a function of my random object. Okay? Of course, it will not be bounded, but you can truncate, and since you control moments and other things, you can remove the truncation. And then show that these fluctuations, which are controlled by these martingales, tend to 0. And that you have it from this. Okay? The fact that you have 1 over k, and this is control. Okay? Similarly for this. Of course, this is bounded in terms of f, but not in terms of the measure, but that's why you also need to control the moments of the total mass. Okay? Here's the same. Okay, let me, just in a couple of minutes or even less. So tomorrow I will discuss a little bit about uniqueness. Okay? Maybe I will make some of the points I have mentioned on the convergence. I will discuss them a little bit more. But let me show you a couple of simulations of this model. So, okay, I have 2 populations. The 2 populations have a special dynamics which is quite simple. So we will assume that each of the populations has diffuses. Each individual of the 2 populations diffuses, so like a random motion, and they have, moreover, some potential. So they are attracted, let's say, to the river or somewhere in the valley. Okay? So I have population 1. I have population 2. So they are very similar. Maybe population 2, I have a steeper potential. So these are quadratic potentials, and what you get, if you just look at the dynamics, that's what we call an Ornstein-Uhlenbeck process. And I will assume that I have a logistic behavior for each of the populations. So here I have space. This is space. Here I'm counting the individuals, the number of individuals of each population. I have a small size population. And they do not interact. Okay, so let us take this as a benchmark or a comparison setting. Okay? So what you expect is to have some growth, which is mild, moderate, because you have the logistic effect. And each of the populations will be concentrated around this, the well of the potential. So here the potential is more steep, so you're more concentrated. Okay? Okay, so this is if I have no interaction, so the population more or less stabilizes, but at the end they will die in any case. And here I am adding a Lokta-Volterra effect from the population 2 on population 1. So population 2 does not see population 1, but population 1 is being killed locally, okay, by individuals of population 2. So that's the. So what you can see is that, okay, I have some survival individuals around, not in the bottom of the well, and well, this population is much smaller at the end than the original one, than the other one, and in the case without the Lokta-Volterra effect. Okay. So the question is, what happens if you help a little bit this weaker population by allowing it to disperse more if it's close to when it's close to individuals of the other population. So this is a cross-diffusion effect on the weaker population. And what you observe is that, okay, it goes down, but not as much as before, and you start seeing some well-defined patterns where I have this my weaker population trying to get close to the well. Of course, it cannot, but it will not become extinguished. I mean, at the same time scale that the other one. Okay? So I can even have some resurrection here, and it will start growing steadily in a way which is close to the original one without interaction. Okay. Thank you.